In this video, we are going to learn about the image processing using convolutional neural network. As you know, convolutional neural network is a go-to architecture when it comes to processing the image data. So as we progress in today's session, you'll understand what is deep learning and you'll understand what exactly is this convolutional neural network, what are the operations that we are going to perform inside this convolutional neural network, and then by the end of this video, we'll take up a use case, a standard use case where we are going to classify the images of cats and dogs using the convolutional neural network, which is a classical task when it comes to computer vision. And also, we are going to perform it in a hands-on manner where we are going to implement this convolutional neural network architecture using TensorFlow. So let's get started and let's start by understanding this main concept, deep learning. Now, before we dive deep into this deep learning, it's very important that you as a learner understand the difference between AI, that is artificial intelligence, machine learning, and deep learning. So this slide talks about the difference between AI, machine learning, and deep learning. Artificial intelligence is actually a system which can sense, which can reason, which can act, and as well as it can adapt as well. It's a computer system which can analyze the overall information, but also it can react as well. So analysis as well as reaction, both are the parts of artificial intelligence system. Now, talking about this machine learning is a subset of artificial intelligence. Now here, in order to analyze the data, in case of machine learning, we are going to make use of statistical models. So statistical models will be used in the scenario of machine learning. Okay, now by making use of the statistical model, I'll be able to learn the patterns that is present in my given data set. And as and when I get more amount of data, I'll be able to learn better about the given representations of the data. Now this deep learning is a subset of machine learning. Here, to analyze the pattern from the given data set, we'll make use of an architecture that is known as artificial neural network architecture. Using this artificial neural network architecture, we'll be able to learn the complex representation in a given data set. So that's the difference between artificial intelligence, machine learning, and deep learning. AI is a system, that is artificial intelligence. It can analyze the information and it can take the action. But machine learning is a subset of AI. It can only analyze the information using the statistical models. In case of deep learning, since it's a subset of machine learning, even this can only analyze the information. Now to analyze the information, we make use of artificial neural network. So that's the difference between AI, machine learning, and deep learning. Now, since this topic, that is the topic of this video, is on convolutional neural network, it comes under deep learning. Now let me give you few more information about this deep learning. So this deep learning, as I mentioned already, it's a subset of AI which will help us to analyze the information. And when we talk about deep learning, here to process the information, we make use of a structure. And this structure is called as artificial neural network. And here, the one that you see on the screen, this is a very simple representation of artificial neural network. Now, in this artificial neural network, we mainly have three important components. One is my input layer, two is my hidden layer, three which is my output layer. Using my input layer, I'm going to receive the input, and this input is received and it will be processed, and this process data is sent to my output layer. So the processing of my input data will be performed in my hidden layer, and the output layer is going to analyze this output from the hidden layer and it will give us the final outcome. For example, if I'm giving this image, that is the image of dog, then I would get the output as dog. If I'm giving this image, that is the image of cat, then I would get the output from this neural network as cat in this output layer. Okay, so this is a very simple explanation about my deep learning. Now here, each circle that you see in my hidden layer, each circle in this hidden layer, so it actually represents a single perceptron. So perceptron is nothing but the basic unit of my deep learning neural network. Now, if I want to talk about this historic concept when it comes to perceptron, so this is how a perceptron would look like. Now, a single perceptron, that is a single cell in my perceptron, it actually performs two things. One is a summation and the another one is called as activation. Okay, so when the perceptron was first proposed by Frank Rosenblatt in the year of 1957, so he proposed the perceptron as it's a perceptron which is a single cell. It is going to receive the multiple inputs, and each input have its own respective weights, and along with that, each perceptron will have its own respective bias term, that is W naught. So in place of summation step, I'll take the dot product between W and I, and on top of this, we'll perform the activation. So historically, when the perceptron was actually created, the perceptron activation function was very simple. I'll check if my summation is greater than 0. If it is greater than 0, I'll give the output as 1. If not, I'll give the output as 0. So that is what we were doing historically when it comes to the concept of perceptron. Now, after that, there were multiple changes happened, multiple researches has happened, and as a result of this, various activation functions have been tried out, and some of the activations that is being used are ReLU activation function, and we have sigmoid, we have tanh. So likewise, we have various activation function when it comes to deep learning neural networks. Okay, so they came into existence of various activation function. So the overall concept is still the same even when we take and when we talk about this deep learning neural network. We'll have the series of perceptrons which are arranged in multiple layers, and these layers are stacked one next to each other, and the data will flow from input layer, passes through the hidden layers, and it finally reaches the output layer. So each circle that you see over here, so each circle represents my individual perceptron. So data starts from input layer, passes through my hidden layer 1, hidden layer 2, hidden layer 3, and finally from the output layer, I'll be able to get the output. So this is how my deep neural network would look like. You can clearly see that I'm stacking one layer next to another layer. So this is the working of my deep neural network. Now, when we talk about this kind of neural network, so this neural network is actually called as feed-forward neural network. Okay, it's called as feed-forward neural network. The reason that we call it as feed-forward because the data is moving forward. The data is moving forward, that is from left to right. Hence, we call it as feed-forward neural network. Now, this feed-forward neural network is awesome. It helps us to solve any kind of problem. But there are some disadvantages when it comes to this feed-forward neural network architecture. One main disadvantage is, so like if I'm using this feed-forward neural network, this would result in loss of neighborhood information. So when it comes to feed-forward neural network, we'll have more number of parameters that we have to optimize, hence training become very less. And if I'm working with image data, then this is going to cause the dimensionality issues. And when it comes to feed-forward neural network, it's not translation invariance. So mainly, if I'm working with image data, guys, so this is going to cause the curse of dimensionality. It's going to cause the dimensionality issues for me while working with image data. Now, in order to mitigate, in order to reduce the errors or in order to reduce the number of dimensions while working with complex image data, we make use of convolutional neural networks. Okay, so convolutional neural networks, in short, we call it as CNN. Okay, so using this convolutional neural network, we'll be able to process the data, that is my image data, in a much more effective way. And the way that I'm able to process my image data is with the help of this operation that is called as convolution operation. So by performing this convolution operation, I'll be able to perform the analysis on the data in a much more better manner. So that's the importance of this convolution operation. Now the question as a learner that you might have is, what exactly is this convolution? Well, to put it simply, convolution, if I'm talking about mathematics perspective, so convolution is a mathematical operation on two functions, f and g, which produces a third function expressing as how the shape of one is modified by the other. Okay, so if I'm talking about in image, to put it simply, it simply means that I'm manipulating the pixel values of an image. Now, I'm sure this would sound too technical if you're hearing for the first time. But let me put it simply, guys. When I say manipulation of the image, it is like adding some special effect on an image. Now just think about it. What will you do when you take a photograph or when you take a selfie? So if you take a selfie in your phone, in your any phone, so first thing that you're going to do is you're going to check whether you're looking good or whether there are any blurriness or not. Now after that, you're going to add some special effect on your selfie so that your look will be enhanced before sharing it on the Instagram or any of your social media handle. Now, what you have done right now is you have applied the special effect to modify the image, and this operation where you are modifying the pixel intensities by uh, adding the special effect on an image, that operation is simply put the convolution operation. So you are already using this convolution operation in your daily life. That's simple it is. That's how much simple it is when it comes to this convolution operation. Now, with this convolution, guys, so I'll be able to better apply these effects on my image data so that this operation is used on the images by my neural network to learn better from the image. Now, before we start applying this convolution operation on image, let me just give you a background as what happens and how does the system stores this image. Now, whenever we store any image, okay, and when we pass it into the computer, my image data, let's assume this is my image data will be saved in terms of pixel information. Okay, so my individual image is stored in the format of pixels. So let's suppose if I have this image of the dimension 50 by 50, I'll be saving my pixels in the region of 50 by 50 region. And here each pixel represents the pixel intensity of each of the color. So that is how I'll be storing the images in my computer. Let's take up a grayscale image. Grayscale image is nothing but a black and white image. If I have a black and white image, so if I'm storing it, okay, assuming that this black and white image is of the dimension 50 by 50, then if I save this black and white image, it will be saved in terms of its pixel intensity values in a matrix which is of the shape 50 by 50. Now here in this matrix of 50 by 50, each element represents the pixel intensity of that particular pixel region. So each pixel represents the pixel intensity. And the value of this pixel will range between 0 to 255. So this is how a grayscale image will be saved. Okay, now talking about color image. Now what happens in the scenario of color image? Well, as you know from your high school, so each color is made up of, or whenever I have a color image, so the color image is made up of three primary colors, RGB, that is red, green, and blue. So I'm getting the various colors in my image is on the basis of color combination of red, green, and blue. So if I'm seeing this color in this highlighted region, this pixel or this color that I'm seeing in this pixel region is on the basis of various color combination of R, G, and B. Suppose if I have a color image which is of the dimension 50 by 50, since my color image is made up of three color channels R, G, and B, then the way that I'll be representing these images is in the format of 50 by 50 into 3, which means each pixel in my 50 by 50 region is represented with the help of three color channels. So this is how we'll be storing the data in the computer while working with the images. So if I'm working with black and white images, it is just height and width. But if I'm working with color images, it will be height, width, and along with that, we'll also have to consider the number of color channels. Okay, so this is the overall working when it comes to this working with color data, that is my color images. Now, before that, we have learned about convolution operation, right? Now, if I have a image data like this, how does our convolution is going to happen? Now, if I have an image data, the way my convolution operation is going to occur is, let's say this is my input region. Input is nothing but my image data. So what I'm going to do is on top of my image data, I'm going to get a kernel. Okay, kernel, you can think of them as a 3 by 3 matrix in this example with some random values associated with it. So I'll take the dot product between my kernel region and my image region. Once I take the dot product between my kernel region and an image region, I'm going to generate the output. Okay, so this output that I have generated, this output represents the transformed pixel intensity of an image. So that is my convolution operation. I'll take the dot product between my kernel region and my input image region to get the output pixel region. Now to put it simply, so just observe this animation. I have an image, and on top of my image, I'm moving my kernel from left to right and top to bottom. And here, the white region that you see over here, this white region represents the transformed region. So here, this white region is my transformed image data, and this highlighted region represents the kernel image, that is my kernel region, where it is taking the dot product with my pixel intensity that is in my image region. Now to help you with the complete information on this, just look at the animation where it would give us the mathematical working example. So if I pause the animation, you'll be able to validate its working. So if I take the dot product between my pixel region and my kernel region, so it is 1 into 0 plus 2 into 1 plus 2 into 2 plus 0 plus 0 plus 0 plus 0 plus 0 plus 0. So 2 into 1 is 2, 2 plus 4 is 6, so 6 is what we have over here. See, that is what is happening when I'm talking about the mathematical operation of convolution on top of my image data. Now, one thing that you might have observed is my image. See, this is my image. So overall, this is my image region. My image region is of the shape 5 by 5. Now, once I perform this convolution operation, my resulting image is of the shape 3 by 3. That means I'm losing a dimension across each axis. Now, as a result of this, my dimension of my image is reduced. Now, why it is happening? The reason it is happening because I'm unable to place my kernel at the center of each and every pixel which is present in my input data. As a result of this, we are losing the dimension. Now, in order to avoid losing of dimension, what is suggested is we make use of padding layer. So this is an animation where I have my pixel region, that is my input region of the shape 5 by 5. As you can see in this given blue region represents my image region. And outside my blue region, I have added one more layer, and that layer is called as my padding layer. So this is my padding layer. Now, what I'm doing right now is I'm placing my kernel on top of the pixel intensity or this pixel region that we have over here. I'm taking the dot product between my this image region as well as my kernel region, and I'm getting the transformed region. So this is my transformed region. Now, if you observe, my original image is of the shape 5 by 5, and even my transformed image is of the shape 5 by 5, which means there is no loss of dimension if I'm making use of this padding layer. So is it clear? Great. Now moving on. Next, we have a stride. Now currently, in all the examples, we are moving one pixel at a time. Now, apart from moving one pixel at a time, here in this example, I'm moving 2 pixels at a time. So as a result of this, you can clearly observe that my original dimension was 5 by 5. Now by using the stride as 2, my new dimension has become 2 by 2. Okay, so stride is nothing but the step size. Now apart from this stride, we also have another kind of layer that's called as pooling layer. Now when it comes to pooling layer, here I'm going to choose a window size. Okay, I'm going to use a window size, and sometimes we also call it as a pool size. Now, by referring this pool size, we can actually choose an correct value for stride, and we are going to summarize the given information. Now, when it comes to pooling layers, we have two kinds of pooling layer, max pooling layer and a average pooling layer. In the scenario of max pooling layer, so I'll take the maximum of the pixel intensities that I have in that pool size or in my pool window. Now here in this example, we have considered the pooling window as 2 by 2 and the slide as 2. So if I highlight this pool, this is my one pooling window. And if I apply a max pooling, I'll take a maximum value. So 12, 28 and 12. So maximum value is 20. So 20 is present over here. If I take the average between those four values, 12 plus 12 is 24, 24 plus 20 is 44, 44 plus 8 is 52. 52 by 4, 4 ones are 4 threes are, so 13 is my average. In the same way here, 32 by 4 is 8, 30, like 30 is the maximum pixel value, maximum over here. So I'll take the maximum of that region in case of max pool layer. I'll take the average of that region if it is an average pooling layer. Okay, so we'll repeat this activity and we complete the average pooling and we complete the processing on the given data. So this was about various convolution operations which we applied on a given image. So to summarize, if I'm constructing any deep learning neural network using the convolutional neural network architecture, I'll have my input image. Okay, on top of my input image, I'll apply various convolution layers with or without padding as per my preference. Then I'll apply some pooling layer. Then I'll again apply some convolution layer followed by pooling. And at the end, once I'm satisfied with the convolution and pooling, I'm going to perform the flattening operation, which is nothing but converting my data into a single dimensional representation and then connect it to a deep learning neural network and at the end connect it to a output layer. So this is how my overall structure of my convolutional neural network would look like. Now, as part of our learning journey in this video, we'll take up a use case. The use case is we are going to classify the photos of dogs and cats. Okay, now this dogs and cats data set is actually a standard computer vision data set which involves classifying the photos as it would either contain a dog or it would either contain a cat. So this is a classical example, guys. So let's go ahead and perform this use case to classify the given images using the convolutional neural network in a hands-on manner. So let's jump back to our Google Colab and let's start coding. Okay, I'm now in my Google Colab. So let's start by importing the data. So in order to make sure that we are able to progress faster, so I have uploaded my file into my Dropbox. So I have already uploaded into my Dropbox. So we are going to get that file from the Dropbox. That's what we are going to do right now. So here I've just mentioned my Dropbox link. So to download the file from the Dropbox. So this is just a Linux command. Ensure that you run this Linux command only from Google Colab. If you run it from your local system, it might not work. So what I would suggest you is, in case if you're not working in Google Colab, just copy this link, paste it in your browser and download it locally, and then you'll be able to extract and do the required operations. Okay, currently I've just got the data. That means I've just downloaded the data. And as a result of this, I'm able to see this catdog.zip file over here in my file explorer. So once we have downloaded it, let's go ahead and let's unzip this. So in order to do the unzip, I'll just simply say unzip. Okay. And I'll mention this file name. Okay. We'll copy the path and I'll mention it over here. And after this unzip, let me just go ahead and remove it because I do not require it. So I'll remove this. I'll just execute this. This will take care of unzipping the data and removing the file. So currently it is doing that activity. Let's wait for it to complete. Okay, it looks like it is done already. So I have a training set and I also have a test set. So what we have done right now is we have just loaded the data. Now it is ready for us to work. Now I'll start by importing the necessary libraries. So I'll start by importing my OS library because we'll be doing some operating system related operation. We'll import NumPy library and along with that I'll import matplotlib pyplot module and I'll import my cbound library and I'll be working with file utilities. So I'll say import shutil. Okay. And along with that, we'll import TensorFlow library, TensorFlow as TF, And I'll also import from TensorFlow, we'll import keras. Okay. Next from TensorFlow dot keras dot models, I'll import sequential model. Okay. Now along with that, we'll be importing the various libraries as well. So from uh, like especially various layers. Okay. So from TensorFlow dot keras dot layers, we'll be importing the input layer, con 2D layer, and we'll also import the flatten layer. We'll import the dense layer, dropout layer, and we'll also import the max pool 2D layer. Okay, so these are the various layers that we are importing. And we'll also import some of the pre-processing functions which are available inside the Keras pre-processing. So from TensorFlow.keras dot pre-processing pre-processing dot image, I'll import load underscore img, and I'll import image to array. Okay, these are the two functions that I'm importing. So this will take care of the important imports for me. Now what we are going to do right now is we are going to set where exactly is my training directory and where exactly is my test directory. So this is my training directory. I'll copy this path and I'm going to say my training directory is this path. Okay, let me just save it over here. Let me just expand this. Okay, so inside my training set I have one more subfolder. So let me just copy that path actually. Okay, so this is my training set, and what we'll do is we'll just go ahead and count how many number of entries that we have inside each folder of cats and dogs. So inside my training set I have two folders, cats and dogs. So we'll count as how many number of images that we have for cats and dogs. So for directory in os.list directory, and I'll be listing the directories in my training directory. Okay, next my path is equal to os.path.join. I'll be joining the path with my training directory. Okay, and along with that, my current directory that I'm getting over here. Next, I'm going to say like this. So dict. Okay, I'm going to create a, like I'm creating a dictionary right here. Let me do one thing. I'm going to say D right here. Okay, D is a folder. I'm going to say cats. I'll write as 0. Okay, and I'm going to mention it as dogs, and I'll initialize it to be equal to 0 for this dictionary D. Next, for dir, so obviously my directory name is cats and dogs. So if it is a cats directory, I'm saying it as dir. Next, I'm going to check the length of my directory, os.list directory of my current path. Okay, now after that, let me just print as well. I'm going to print as the number of images in, I'll mention it as dir. Okay, folder is. Then I'm going to write it like this, dir. Very simple, guys. That's it. So dir, and this will display the number of images that we have right here. Now, if I execute this, so it is giving me the output that the number of images in the docs folder is 4006 images. That's great. And number of images in cats folder is 4001. So that is what we are able to see over here from this function. So we have 4000 images for cat and like 4001, and we have 4006 images for dog. And that is what we observe. Now let's just create a Seaborn's bar plot. Okay, I'm going to say sns.barplot to get the visual representation of these numbers. So sns.barplot, and I can simply I can mention it like this. Okay, I'll write as, so I'll define my x. My x is nothing but the names that I have. I'm going to say cats, dogs. Okay, and I'll define my y is nothing but my Python list. Inside my Python list it is cats. Okay, since it's cat first, d cats, d dogs. Okay. Next, I'm going to say sinus dot bar plot x comma y, and let's say plt dot show. So this is going to give me the visualization of my bar plot, which tells me as what is the frequency of the images of cats and dogs in the given data set. Okay, now to get a better understanding of the images that we are dealing with, let's do one thing. Let's create a function which will display the images that we have. In order to do the same, I'm going to define a custom function. I'll define my custom function as def display image. Okay, this will take my image directory. Okay, the way that I'm going to do is I'll write as I is equal to 1. Okay, this is the initialization. I'm going to define my plt dot figure, that is I'm specifying my figure size to be equal to, let's say, 10 comma 10. That's my figure size that I'll be using. Now I'm going to say for image in image directory that I have. Okay, I'll say plt dot subplot 1 comma 3 comma I. Okay, next plt dot axis, I'll mention it as false because I don't want to display any axis right here. Next, I'll simply say im show img. Okay, so I'll simply call it as im show img, and then so it's actually plt dot im show, guys. Okay, plt dot im show img. Next, I'll increment the value of by 1. Now after that, plt dot show. So this is going to display the images from a particular folder. Now, what I'm going to do right now is I'm going to just display three images for cats and dogs for the demonstration purpose. The way that I'll be doing is for my directory in os.list directories, I'm listing the directories of my training directory. Okay, I'm listing the images or the folders that I have in my train directory, and I'm going to mention that my image path is equal to os.path.join my train directory, comma dir. Okay, I'll mention my count is equal to 0. Now after this, I'm going to say that my image directories, okay, image directories is my blank Python list. Next, what I'm going to do, I'm going to say for I comma image in enumerate, and here I'll mention my os.list directories. Okay, my IM path, that is my image path that I've got. So this is going to give me the each and every individual image that I have with me. Now what I'm going to do is I'm going to join this image. So I'm going to say that my image path, okay, my image path is equal to os.path.join, and I'll join my image path that I've got on top of this image ID that I've got. Next, this image directories which I have saved right now. So I'm going to append it. So image directories dot append img underscore path. Now, what I'm going to do, so I'm going to say that if, since I'm selecting only first three images, if my I becomes 2, I'm just going to apply the break statement right here. That's it. Now, after this is done, next thing that I'm going to do is I'll come out of this for loop, and I'm going to call my display images, and I'll send in this img dirs. Okay, so this is how I'm calling. So this display image is the function name. So let's execute this. All right, so it looks like we have img dirs. We are getting some error. Let's validate it. Okay, the reason that we are getting this image because here we are making use of plt.imshow. Now let's do one thing. plt.imshow supports only the numerical data. Now in order to display from the path, we'll import the imshow from the sky image. So I'm going to say from skimage.io, we'll import imread as well as imshow. Okay, now instead of plt.imshow, I'll simply call imshow. Now this should work. So we should be able to see the visualization. See, this is the sample three images of dog, and this is the sample three images of cat. Okay, we have displayed the images of cats and dogs. Now, what we are going to do is we are going to split the data set into three parts. 70% of the data, I'll keep it in my training. 15% of data, I'll keep it in my validation. Another 15% of data, I'll keep it as a test data. Okay, now in order to do this distribution, we'll make use of the original, the OS module itself, and we'll do the distribution from our end itself. Okay, so we'll follow a very simple technique and we'll complete the splitting from our end. In order to do the same, I'm going to say it like this. So we have already created our training directory. Now I'm going to say that directories is equal to, I'll split into three parts: train, validation, and test. Okay, train, test, and validation. These are the three directories that I'm going to create right now. I'm creating it as a Python list. Now I'm going to specify my root directory. Okay, root directory is, this is a directory in which I'm going to pass all the, like I'm going to create the subdirectories. Okay, root directory is my data dir that I'm going to create. Now I'm going to say that if not os.path.exist. Okay, what is the directory? That is root directory. If the root directory doesn't exist, then I'm going to say that for d in dirs, I'm going to say that os dot mkdirs and os dot path dot join root directory comma d. Okay, I'm just going to create the subdirectories inside my root directories. Now, once this is complete, next, what I'm going to do, I'm going to use the similar logic, guys, for dir in os.list dir, and I'll specify my training directories. Okay, this is my training directory, and I'm going to use the similar logic. I'm just going to join the same. I'll say that de is equal to os.path.join root dir, comma train. Okay, and I'll mention my dir. Okay, so I'll just create some directory over here. Next, os.mkdir, and I'll mention it as de. I'm going to create a directory over here. Okay, now once I create a directory, the next thing that I'm going to do is I'm going to do some random selection, and I'll copy the image and I'll remove the original image. So I'll just copy and paste the code that I have already written. So this is going to select the random image, and then it is going to copy the files to that specific folder, and we'll repeat this activity for the training data and the validation data as well. So we'll just go ahead and repeat this activity, and once this is done, we'll just execute this. Okay, so we'll just go ahead and execute this. So here we are getting an error, so has no attribute mkdirs, so it should be make dirs. Okay, it is actually make dirs. So this is done. So what we have done right now is from the training directory itself, we have splitted the data into three parts, and it is present inside my data directory. So 70% are in training data, the few remaining 15% are in test data and the validation data. So we have defined the individual path. Next, what we are going to do in order to enable my model to load the data from this folder, so we'll make use of image data generator from the Keras library. So I'm going to call my image data generator. Now, in order to call that image data generator, first thing that we have to do is we'll have to verify whether we have imported it. So let's go ahead and check whether we have imported it. So we have not imported it. So let's go ahead and import it, and then we'll create the object for image data generator. So in order to do the same, so first thing I'm going to do is from TensorFlow dot pre-processing
dot image will import image data generator. Okay. Now, once we import, that means once this import is complete, TensorFlow dot preprocessing dot image. Okay, it's actually dot keras. Okay, once the importing is done, we are going to create the object for training data generator, validation data generator, and test data generator. So train data gen is equal to image data generator, and inside the parenthesis we'll specify the rescale as 1.0 divided by 255, comma, I'm going to do some rotation as well. So I'll specify my rotation range as 0 0.3, and I'll mention my zoom range as, let's say, 0 0.2. So this will actually help us in augmenting my image. So horizontal flip as true, and I'll also specify my vertical flip as true. Okay, so this is how I'm generating my image data generator. Now on this train data generator, I'm going to generate my train data. So I'm say train data gen dot. I'll have to flow from directory. Okay, my directory is nothing but my trained, that is this directory. So this is my training directory, and we'll have to mention what is the class mode. Okay, I'll mention my class mode is equal to binary. Okay, this is my binary class mode, and I'll set a target size. Okay, in this demonstration purpose, let's say I'm going to resize it to a specific size of 224, 224. So this is going to generate my train data object. Okay, now what I'm going to do is let's look at the train data classes. So if I say train data dot class indices. So the train data class indices is cat is 0, dog is 1. So what I'm going to do, I'll do a dictionary comprehension. So to do this dictionary comprehension, I'll mention it as my class ID is equal to, I'm going to say that for I comma j in trained data dot class indices, okay, dot items. This is going to get the items in the pair. Then the way that I'm going to say is I'm going to invert my key value pair. So j colon I. That is what I'll be doing. Now, as a result of this, if I display my class ID, so I'll have the inverted value. So 0 for cats, 1 for dogs. And similarly, we are going to do the similar activity for validation data as well. So I'm going to say valid data generator is equal to image data generator. In this scenario, we'll simply perform the rescaling. We are not interested in doing any of this like augmentation of this data. Instead of train, I'll change it as validation over here. Okay, so instead of train data, it should be val data. I'll repeat the same thing for the test data as well. So test data gen, test underscore data, and instead of val, it should be test now. Okay, so we have created the objects for the training object generator, validation generator, and the class IDs and the training as well. The next step is obviously building the model. Now here to build the model, first I'll define my model as sequential. So since we have already imported, I'm going to define my model as sequential. Now in this sequential model, so I'm going to add my individual layers. So I'll say model.add. I'll mention my con2D layer, and I'll specify the filters. Okay, filters is nothing but the number of kernels. I'll mention my filters as 16. My kernel size is equal to 3 comma 3. Okay, and let's mention our activation is equal to ReLU, And more importantly, we'll also have to specify the input shape. My input shape is 224 comma 224 comma 3. So this will be my input shape because here we are dealing with the image data which is color in nature. Now on top of this convolution layer, I'm going to add one more convolution layer. Let's say con 2D, and I'll mention filter size 32, and I'll mention my kernel size as same, and I'll also use the same activation function, that is relu. Now once this is complete, I'm going to add some pooling layer. So model.add max pool d, and we'll mention our pool size is equal to 2 comma 2. Okay, now after that we'll go ahead and create some more convolution layers. Okay, so I'll just paste it over here. I'll modify the number of kernels this time as 64, and on top of it we are going to add some pooling layer. Next, I'll set the number of filters as 128. Okay, on top of that we'll specify the pooling layer. Okay, let me add this pooling layer. Now after I add this pooling layer, to avoid the overfitting of the model, we'll say model.add, we'll mention dropout, and I'll specify the rate as 0.3. Okay, so this is how I'll be specifying my dropout layer. Now after I am satisfied with the convolution operation, I'm going to say model.add, I'll specify my flatten layer. Now, once I perform this activity of flattening, I'll connect it to my dense layer. So model.add dense, I'll mention my units as 64, and I'll mention my activation is equal to relu. Now, after this, let's say after this dense layer, I'm going to add one more dropout layer with 30% of dropout. Now, at the end, I'm going to add a single neuron with activation of sigmoid because this is a simple binary classification task. Now, at the end, I'll display the summary, and this will display the overall model summary of the model that we have just created. It's a sequential model. We have the series of convolution pooling, and at the end, we have the final layer. Okay. Now, once we have the model ready, the next thing that we have to do is we'll have to compile it. Now, in order to compile the model, I'll say model.compile. Inside the parenthesis, we'll specify the value of loss. Loss is equal to, I'm going to mention tf.keras dot losses dot binary cross entropy. Will make use of binary uh, cross entropy. This is the loss that I'm going to use, and I'll use my optimizer is equal to Adam, that is the given optimizer that I'll be using, and we'll simply use the metrics as accuracy. Okay, once the model compilation is complete, we can go ahead and perform the training. Now, what I'm going to do this time is, before I do the training, I'll implement the model checkpointing, which is my callbacks. So, from TensorFlow dot keras dot callbacks, okay, I'll import model checkpoint, and along with that we'll also import the early stopping. So I'm going to say yes, that is my early stopping. I'll configure my early stopping to monitor val accuracy. Okay, and let's say patience is equal to 4 or 3. Okay, minimum delta is equal to 0.01, and I'll use the remaining settings as it is, and I'll also see model checkpointing. So model checkpoint. So we are going to specify the file path. I'll mention my file path, and my file is best model cnn.h5. This is the file path that I'll be using, and I'll monitor the same validation accuracy. Okay, and I'll also say one more thing, which is called as save best only is equal to true. So I'll define my model checkpointing, and once this is done, I'll define as callback, which is a Python list which contains my both early stopping as well as model checkpointing. Now let's go ahead and let's perform the fit on the data. I'll say history is equal to model dot fit underscore generator, and inside the parenthesis I'll specify my generator is equal to my train data. Okay, my validation data is equal to my val data, and for the simplification purpose I'll say validation steps is equal to 32. Okay, and I'll say steps per epoch is equal to 30, let's say 64. Okay, let's use the steps per epoch as 64, and I'll mention my number of epochs as 30, which means I'm just doing the fit on only limited amount of data, guys. Okay, callbacks is equal to callback. So in order to increase the training time, I'm just going to train my model like this. So this will take care of model training. We'll wait for a while and we'll do one thing, guys. So in this scenario, currently, the system is taking more than 6 minutes to train a single epoch. Now, what I'll do is I'll just enable the GPU. So let's enable the GPU and let's rerun the entire code so that we are able to perform the training in a faster pace. So it is initializing again. So we'll have a GPU enabled work system. So now I'm performing the fit. Now let's wait for the training to complete. Now in the meantime, what I'll do is let's create the visualization. I'm going to say my hist is equal to history dot history. This is going to generate my dictionary for me. Now on this dictionary, I'm going to create the plot. So plt.plot, and I'm going to mention my h accuracy. That is my hist objects accuracy. Okay. And along with that, I'll also print the accuracy, that is my validation accuracy, to get the visualization of my accuracy on my training data along with that accuracy on my validation data. Okay, so this will help me to understand how the validation like how the accuracy is getting changed. Now at the end we can also perform the evaluation on the model. So in order to do the evaluation, let me just write the code over here. I can say model dot evaluate underscore generator. Okay, and here I can specify my generator. My generator is my test data. Okay, I can generate my test data, and this is going to help me to evaluate my model with my test data. So currently the first epoch is completed and the accuracy from the first epoch is 51%. And let's wait for the training to complete, guys. So we have set the number of epochs as 30. Let's wait for the training to complete. In the meantime, what I'm going to do is we are also going to uh, like prepare the evaluation as well. So what should happen if I want to test it? So let's wait for the execution to complete. And by the time the execution is complete, I'll also show you how we can evaluate by giving a new image. Okay, so the training has been completed with just 4 epochs. It could be due to the callbacks that we have mentioned. Now, after that, here, this is how the visualization would look like. The visualization for training accuracy and the validation accuracy. And here when we evaluate it on the test data, the accuracy that we are getting is just 52%. So we still have to improve the model. Now here a custom code has been written where I'm selecting the image in a random manner. Now once I select the image in a random manner, I'm just generating the prediction from the model that we have trained. So once I executed this, the input image is this, obviously clearly an image of cat, and the prediction from my deep learning model is cat. So what we have done in this video overall is we have seen how to train our deep learning neural network using the convolutional neural network architecture, how to fetch the data, and we have also understood about the various operations that takes place in the convolutional neural network, and we have implemented an end-to-end code from scratch. I hope you enjoyed it. I look forward to seeing you next time. So till then, take care, guys.